Hi everyone, Michael here again. So to kick us off, I'm just going to go over what's new. Obviously, there was a big release for vLLM. We had 0.5.1 last week. We supported a lot of new models that we'll go into more detail later on, and initial support for pipeline parallelism, which is a really big feature. Not performant yet, but it'll be especially important for some of the big 400 billion wink wink models coming soon. And we have many updates to FP8, which, as Sasha mentioned, Cody and Philip from Anyscale will be going over the current state in vLLM. With respect to office hours, obviously today, welcome our first sort of guest speaker. And we'll be having guest speakers for the next couple of office hours with folks from Neural Magic and folks from Roblox. So look forward to those in the next bi-weekly office hours. So without further ado, let's get into the meat and potatoes. For those of y'all who don't know here, we'll talk about vLLM. It's easy, fast, and frankly, the most used open source LLM inferencing library, or rather kind of serving library. It has interfaces both for offline usage, for batch processing just in pure Python with the LLM engine, for getting really good batched token throughput. And it also has a really performant and easy to use OpenAI compatible server with support not just for text generation, but also for vision language models and embedding models that we're adding support for all the time. And yeah, lots of GitHub stars, lots of downloads, and lots of contributors beyond just Neural Magic and Anyscale here, both from commercial companies and also from community and community users like you. It supports a wide range of models and new architectures that get announced and dropped in research papers, releasing them. Generally get supported day one, including some of the latest MOE models like DeepSeek V2 and Fun2, which was great to see. And we have a large support of hardware architecture. So we obviously do a great job at supporting NVIDIA GPUs. But we have a flexible backend that supports AMD GPUs, AWS accelerators, Google accelerators, and initial support for a variety of CPUs. So we're always accepting new hardware architectures, and generally we have this flexibility because we're built sort of on this easy to use Python and PyTorch based API. We also have a large number of inference optimizations, quantization, of course, for model weights and activations, but also inference serving optimizations like automatic prefix caching, hosting, and usage of multiple LoRa's for batch LoRa inference, for supporting fine-tuned models very cheaply and with great latency. And supporting lots of parallelism to scale up your model and hardware deployments to meet your latency SLAs through tensor parallelism and pipeline parallelism. So following that, here at Neural Magic, we're really focused on making open source LLMs and vLLM great and bringing those to every enterprise on the planet. We build enterprise-supported inference servers, and so this means we build supported distributions with stable versions so that we can hotfix versions of inference server software that you're deploying on your infrastructure and offering a lot of support, telemetry, and dashboards alongside that. We also work to help you right-size and profile your deployment so you understand not only how to configure your hardware and configure your software, but also how you should be optimizing your models or compressing them to hit your performance metrics. And we build, alongside working on vLLM, we build optimization libraries like SparseML and LLM compressor to help you compress your models as accurately as possible while getting better performance. With all that said, I'd now like to pass it off to our folks from Anyscale, Cody and Philip.
Hey, I'm Philip. Let me first tell you a little bit about Anyscale. Our mission is to make it very easy for companies to build out their AI capabilities without needing to worry about the underlying infrastructure. We are the company behind Ray, and we love open source. We've also been contributing a lot to vLLM, things like multi-LoRa, speculative decoding, chunk prefill, FP8 support, and more. I want to give you a little overview over our product. So it's a managed compute platform on top of Ray. It provides workspaces, jobs, and services. Workspaces are a development environment. It's backed by a Ray cluster, and it provides all the fast development iteration capabilities, IDE integration, code integration, persistent file handling, and things like that. Jobs are for batch workloads like training workloads or batch inference workloads, and services are for online serving like arbitrary models or vLLMs, LLMs, and all of these concepts are backed by Ray. So it's all scalable, and it provides different AI workloads. I would like to invite you. We are actually hosting a vLLM track at our annual Ray Summit this year in October in SF. And if you want to join, I'd love to meet you there. And there's a link in the slide.
Awesome.
So let's now change gears and talk a little bit about FP8 support. First, I want to give a little motivation on why we should care about FP8. I actually think about FP8 a little bit less like a quantization scheme and more about the next step after FP16. And it's just a very natural data type to do. People actually also use it for training and also for inference. It brings a lot of value. So in terms of memory, obviously the weights and activations only take half of the memory compared with FP16. So this means you can store larger models and larger context sizes for a given amount of GPU memory. That's one benefit, but also many of the LLM operations are memory bound, especially decoding. And so these will also get faster because now you need to load less memory. So that's on the memory side. On the compute side, actually, the recent GPUs all have native support for FP8 computation. So the computation will also get faster. Like H100s support FP8, L4 support FP8, A300, MI300 supports FP8. And the FP8 compute throughput is twice the amount of the FP16 compute throughput. This is the table from the H100 NVIDIA. While these are, you have to divide these numbers by 2, the ones that have a superscript 2, and because they are for sparse sparsity. But you see that the FP8 throughput is twice the amount of the FP16 throughput, and we also measure that in practice. So it's very good to speed up the compute. And then also in terms of accuracy, it's a great choice. Actually, with appropriate scaling factors, FP8 can get very similar model accuracy as FP16. And especially for transformers, actually, FP8 is a better choice than other 8-bit quantization schemes like Int8. And also going forward, I expect more models to be trained natively in FP8, and then you will get zero degradation in terms of inference performance. Cool. I'll hand over to Cody to dive a little bit more into the technical details about FP8.
All right, thank you, Philip. So yeah, Cody here. So I'm currently I'm going to dive deeper about FP8 implementation and especially in VR and how we use that. So first of all, I want to introduce 2 data types in FP8. We usually use 2 different formats to represent 8-bit floating points. That could be E4 and 3. That means the 1 sign bit plus 4 exponent bits and 3 mantissa bits. You can imagine if because we have 4 exponent bits, you can have the value range from -448 to +448. And you can also see that there's a less exponent bits, but more mantissa bits compared to another format I'm going to talk about. So this can preserve higher accuracy than the other format. So it's commonly used for forward pass to store the activation or the model weights. But the problem is because you have the last exponent bits, so you probably need to scale the number before casting to FP8 to maintain the accuracy. So here is an example. The X is the input tensor, which is in FP16, and Y is the output tensor in FP8. You have to first calculate the scaling factor using the absolute maximum value of your tensor and scale all the values and then cast to FP8. The concept behind this is to move the Mantissa parts to the exponent part and then cast to FP8 so that you can reduce the accuracy loss when cutting out those Mantissa bits. Another format is called E5N2. You can see this. This just changed the number of bits for exponent and Mantissa. So you can have a larger value range from minus 57K to the positive 57K. So this can offer a larger interval range, and this is commonly used for backend pass for training because usually you will have a larger value of the gradients. And because you have the same number of bits, same number of exponent bits to the FP16, you may not need scaling factor because of that. So simply saying casting from the FP16 to FP8 E5M2 could be more efficient because you just need to cut out the Mantissa bit without changing the integer parts. Next slide, please. Right. So now that I'm talking about the FP8 in the latest VLLM 0.5.1, in terms of the FP8 quantization activation, we have two quantization schemes. The first is called the dynamic scaling. That means we can calculate the scaling factor on the fly when you're running the model. This is more accurate and do not need calibration data because we just quantize the tensor based on what the current tensor is. But this actually will bring the significant performance overhead because you have to see all the values in this tensor and calculate the scaling using the equation in the previous slides, and then apply that to all the values in the tensor. So the overhead of this on-the-fly dynamic scaling usually it's most benefit from FP8 speed-ups. So we actually prefer more on the static scaling. That means we will have a collaboration data and use the offline quantization to figure out a scaling factor for each activation in each linear layer or MOE layers. And then we keep that scaling factor in our FP8 checkpoints, and then you just use that scaling factor constantly in our runtime inference. So this could cause some accuracy issue, but we will show that this accuracy issue impact is actually pretty minor, but this will moderate the performance overhead a lot.
Can I say a few more things about the dynamic scaling? The places where this is very useful is, first of all, if you don't have an FP8 checkpoint for your model, we actually support just loading from FP16 and then converting the weights during loading time and then using the dynamic scaling. So like it works out of the box for a wide variety of models. And I also found it very useful for if you want to quantize your own model for comparing the accuracy. It's because the scaling is done at runtime, it basically tells you like what is model performance that you can expect if you do a very good job at determining the scales. And so like in a way it gives you a bound on how well your scales can do. So it's often a very useful tool to evaluate how good the FP8 checkpoint actually is.
Yeah, thanks Philip for notes. So now I'm going to briefly talk about the FP8 checkpoint structure. Now we use in the VLLM, and we hope this could be a standard across the industry for this format. So the format I take from the example is from the mixture 8x7B. This is the MOE model. So we can see in this table, in the attention part is actually the same as the normal transformer dense model. For the QKV and output projection, we have the weights stored in FP8 E4M3 format, and we also store the input scale, weight scale, and the KV scale. So you can see all the scales are just the floating scalar values stored in FP32. And then for MOE layer, we have a gate before the MOE weights, MOE experts. And you can notice that the weights, the gate is actually still keep in the BF16 instead of FP8. This is because of the implementation limitation, because the current the FP8 matrix multiplication kernel from NVIDIA or AMD, they require the input shape to be divided by 16. But most of the MOE models only have 8 experts. So that means we have to pad 8 experts to 16 experts to eat all the performance benefit from FP8. So we currently keep in FP16. But hopefully this limitation can be removed so that we can get another round of speed up in the MOE model. Yeah, and the rest are the experts for W1, W2, W3. The same as the previous. The weights are in FP8, and there's corresponding input scale and weight scale. So this is checkpoint structure, and you can see the for example from the Hugging Face Hub, where Neuromagic guys already uploads tons of the FP8 checkpoints for the popular models. And then I want to talk about a little bit about the supported metrics for FP8. Sorry, can you go back to the first slide? There's the no worries. Yeah, there's the FP8 support metrics for NVIDIA GPUs. For layers, we currently support FP8 computation in linear and MOE layers, and then we are working on attention layers to be computing FP8 as well. And we also support KV cache in FP8. This supports both formats, E4M3 and E5M2. And the E5M2 FP8 KV cache is actually kind of useful if you're running the inference on previous GPUs like A100 or like older versions. In this case, the FP8 KV cache is only used for the storage purpose. That means you can shrink the KV cache size by twice, but you won't get any computation benefits. And currently in vLLM, we support the model running on FP8 for Llama, Q1, Mixed-Rank, Q1, 2. You're welcome to add more models to the FP8 support. It's actually quite straightforward. We just haven't bumped the model coverage at this moment, but we'll definitely get into that very soon. Next, please. All right, so let's look at some quality performance results for FP8. So the first figure on the left top, this is a quality results compared to FP16 using the LLM, open LLM evaluation. This is the same benchmark as used for the Hugging Face leaderboard. So we can see basically there is a less than 1% drop in the accuracy with the static scaling factor. And this quantization process is actually pretty straightforward. We just use the open public data set for like 2K samples to do the quantization. So the quantization is actually pretty fast and it's pretty accurate. And we can see the left bottom figure. This shows the Llama 370B FP16 versus FP8 performance for the offline batching. And you can see we can achieve like overall 1.5 performance improvement in this case. And then for the two figures in the right-hand side, we show the ITL, inter-token latency, or 1 divided by this will be the token generation throughput. We can see like 1.50 to 1.8x improvement for the Llama 70B model or the general dense transformer model. And then we can also see like a 1 to 1.65 improvement to the MOE model. Yeah, we're still working on improving this MOE kernel to make it work better for the low QPS or small batch sizes. And I want to know that in order to achieve this result, this will require the Triton 2.3.1. And the current latest release of vLLM depends on the version 2.3.0. So you might need to manually upgrade that after installing the vLLM, or you can wait for next release. We will upgrade the dependency. Next, please. All right. So lastly, I want to introduce like how to getting started with the FP8 in vLLM very quickly. This example shows how do you host a Llama 370B instructor model on 4 H100 GPUs. There's two ways. One is to launch an OpenAI API compatible endpoints using the command I shown here, like of course after you install the vLLM. So this command will actually launch an OpenAI API server on, for example, the local host with the port 8000. And then you will serve the model 70B with the FP8 with the tensor parallel size 4. So after you launch this endpoint, you can just use the OpenAI SDK or the same protocol to query this endpoint, and you will get the result. Another use case is definitely like a batch inference. You can just write a Python script like this, and then you can load the model with the tensor parallel 4, and then you can just call model.generate to directly get inference results. And then in the right-hand side, there's some FP8 for vLLM that you can directly use at this moment. If the model you're interested in is not listed here, you can definitely use the auto FP8 to quantize that by yourself. And again, this is extremely easy, so highly recommend you to play with that. Finally, is the future or actually this ongoing roadmap for us to keep improving FP8 invariant support. First is the FP8 WA16 support for the Emperor architectures. Because the Emperor architecture like A10 or A100, it doesn't have the native FP8 support in terms of the computation. So, but we can still use the FP8 checkpoint to save some memory footprint. So in this case, we'll keep the weights in FP8, but we'll keep the activation in FP16. We can still get benefit, especially for small batch sizes, because it's memory bound. So if you can reduce the memory by half, they'll be still super helpful. And then, like I mentioned in the beginning, we are also working on the FP8 attention for ADA and Hopper architectures with the native FP8 support using the flash infer. So those are the ongoing works we're working on. Next, please. Yeah. So I think I'll hand back to Michael for general year-end updates.
Yeah, thanks for that great overview. I know we're all super excited to have more people use FP8. So yeah, please give it a try and let us know how it goes. I'll make sure to go pretty quickly through what's new in 0.5.1 since there's a lot, but please feel free to ask questions and have us go back to give you more detail on these things if needed. So as mentioned before, some of the big features are pipeline parallelism being added. This is an important type of parallelism that allows us to essentially split the model into sort of depth-wise into separate chunks and put them across different GPUs or different machines or nodes eventually. And this allows us to essentially not really optimize for latency, but do some greater optimization for throughput, since the different pipeline parallel sections can essentially run in parallel. There's several models supported. Gemma 2, which is obviously a big model from Google. Currently that requires, or rather the 27 billion parameter checkpoint requires running with flash attention, since we need that for soft capping of the logits. Jamba is finally supported, which is important because it's the first state space model with non exponential attention required. This is an important point towards supporting more models like this. There's also support for DeepSeek v2, which is a really important MOE model that hopefully you've seen at the top of model leaderboards. And a lot of work has gone on to continue making progress on vision language models, notably supporting V3 vision, which is a really capable model for how small it is, and dynamic image size, which is particularly important to make it a lot easier to use the vision language model interface. There was a lot of support in improving the quality of the TPU support, which was initial in 0.5.0. And is getting stronger over this release. There was also an OpenVINO backend merged, although that's initial. We finally added support for sharded tensorized models. This can offer up to 2x improved model loading from disk or from S3 buckets if you pre-shard your model for tensor parallelism. So this is important for services that need with like faster model server startup. And we had some improvements to the OpenAI usage statistics that I think that's even better than OpenAI's API now. In terms of performance, there were a lot of improvements in general performance, particularly for tensor parallelism. That we're targeting, latency for tensor parallel H100s. We also added support for a lot more quantization methods to compress tensors, which is a new quantization backend from our LLM compressors library that we're developing. There were a lot of optimizations on FP8, as mentioned before, including making the overhead of quantizing less. Cody worked directly on this, doing some nice little CUDA trickery. I worked on the FP8 Marlin support, so starting to bring FP8 to Ampere GPUs and GPUs that don't have hardware support just through weight-only quantization. This just barely got in. And we also have support, pretty wide support for Flash Infer now, both on prefrontal decoding with CUDA graphs. There's still some features that aren't supported in the back end, but we'll be expanding those, and that will hopefully be the first place that we add FP8 attention, as Cody mentioned. A lot more work on speculative decoding. There's sort of ongoing work there in improving performance, and getting rid of overheads, generally, between all the sort of scheduling overheads that speculative decoding makes stick out. But a lot of work there, so that's particularly a good place for a contribution if you're interested in finding a nice project. And several development productivity things. The one I will note is sort of the perf.vlm.ai. Check out the dashboard, and you can see some of the performance metrics and how they change over time as we make improvements to vLLM on a commit basis. One thing I want to call out before we move to questions is issues and RFCs that we have. As I mentioned before, there was a lot of refactors to vision language models, and there was a guide published in our documentation for adding support for new ones. So that's particularly a place where some of the less popular vision language models, if you have a use for them and want to support them, please check out the guide and take a look at contributing it. And we have several RFCs here that still could use more help, such as optimizing speculative decoding. Now there's various backends for them, particularly optimizing CPU support, since we still have a pretty rudimentary Intel and AMD CPU support. We could definitely pull in some more optimized implementations of attention or quantization. We definitely could see more usage of embedding models. Currently, we only support Mistral models, and I am working on supporting Qwen 2 models for embeddings. But there's a lot more models like we use for embeddings, especially encoder-only models like BERT and other models in sentence transformers that we could pretty quickly host in vLLM with the right support. And several things that would help, improve serving, including getting flops estimation to understand, what's your MFU, or are you getting full utilization of the hardware you're using on your inference server, and more sort of sampling features with all the mirror-stat, quadratic sampling, fancy stuff. So without further ado, let's get into the questions. We'll go over some questions that were asked ahead of time. If you recognize the questions you asked, feel free to jump in and ask them properly, so we can address you directly. Otherwise, we'll try to handle these in the general sense. And feel free to start asking questions in the chat. And this is where we kind of open up, and you're free to put in text or start talking. So the first question asked ahead of time was on FP4. Yes, we will support it. No, there's not really hardware support for FP4 yet. So this is why it's not a focus. If we would implement it, it would just be for weight-only quantization. And we already have sort of int4 implementations that do a pretty good job. Obviously, the new NVIDIA Blackwell or rather B100 hardware and the AMD MI350X, that both of these should come out at the end of this year or next year, will have support for supposedly for FP6 and FP4. And we're working directly with those companies to hopefully have really good support for FP6 and FP4 there. And then any opinion on the 1-bit or 2-bit models, kind of called 1.5-bit? That's the log 2 of 3. Yeah, we definitely don't have, we do have support for 2-bit quantization through AQLM, but I think you're specifically talking about maybe the HQQ method. And this, again, is sort of weight-only quantization. So it won't give an improvement in, compute-heavy offline throughput or compute-intensive serving throughput. So we're a bit more focused on weight and activation quantization right now with FP8 and Int8, since there's hardware support for those formats. But we would totally be open to a contribution of this backend, and I'm sure I think there's an issue actually already open for the HQQ quantization, which is this 1.5-bit quantization and quantization technically. When you get that low, it's just palettes all the way down. There's a question here on freeing up memory. So basically, like when you make a model through vLLM, it will, of course, allocate space for your model and load it into memory, and then it will allocate up to 90% of your GPU memory by default. You can control this with the GPU memory utilization parameter, but it will pre-allocate most of your GPU's memory for KV cache space for performance purposes. So if you want to make another LLM after making an LLM, you need to delete the object and additionally probably free any PyTorch memory. We do have an RFC for making sort of a scoped LLM class so that you can sort of work with that, allocate within a with statement in Python a new LLM, and once you get out of that, it will free up. We use this a lot in our testing, since obviously we're testing a lot of models in PyTest. Essentially, there's a lot of places you can look in our code for how we clean this up, but generally you want to delete and do any garbage collection for the LLM before you move on to a next one. This is an interesting question. We saw a significant throughput advantage on a 4x A100 40 gigabyte system versus a 2x A100 80 gigabyte system for Llama 370B. Any idea why this might be? So obviously we have the same amount of memory here, but we have different amounts of compute and possibly memory bandwidth available. So particularly in a place where you're talking about throughput and you're probably running with a large batch size, the extra compute from having multiple GPUs, but the same amount of memory, means that you have more flops to crunch through the computations needed for these heavy batch forward passes. So it makes sense why you would get greater throughput here. There is also maybe a memory bandwidth difference here, since the 40 gigabyte model uses different memory configuration than the 80 gigabyte model, but this is probably a little bit less pertinent here, since we're considering we're talking about throughput, we're probably talking more about a compute bound workload, less so than a memory bound workload. Another question here is, we've seen an inverse relationship between token generation throughput and request throughput. How can that be, and what kind of tuning can we do to optimize request throughput? This would be a great one for the person to step up on, as it's a little bit hard to talk about generally. Obviously, it depends on what's your distribution of input tokens and output tokens in each of your requests, and how is that working, how is that changing over time? Definitely as you get more requests coming in and you get larger batches, during during continuous batching inference, your inter-token latency will decrease. So you're essentially making less progress on the output generation for each request, but you're processing more requests at the same time. I say this, it should result in more request throughput, but it will affect and make the per request latency worse as you get greater token generation throughput. This is kind of a bit complicated. Some of the things we would talk about here is, looking into quantization methods or increasing tensor parallelism so that you have more compute to go through, and possibly more memory bandwidth to, decrease, the latency that you're having per request. And in addition, look at tuning your, I forget the specific name, but there's a parameter like max num batched requests that will hopefully keep the number of requests you have batching a lower number, so that your inter-token latency can be, faster, and as you can keep up with the requests that you are processing, and maybe keep more requests that are trying to interrupt your current batch of requests a little bit.
Actually add a bit more about this. Basically, Mike already covered most of the thing. I want to just like a quick summary of this. So in terms of the vLLM mechanism, basically, it's actually the prefill first a scheduling policy. That means when you're decoding a batch of requests and there's a new request coming in, we will prioritize making that request prefill first and then join the decoding batch together. So your ITL may be interrupt if there's new requests keep coming in. There's another good feature called trunk prefill. This will resolve this issue somehow, because when you enable trunk prefill in the vLLM, the scheduling policy becomes the decoding first. So that means we will keep the decoding request on the loop all the time. So you won't be interrupted during that. This is the first thing. And the second is if you enable trunk prefill, it's likely that your decoding process will become the compute bound if you allow the large trunk, because you're attaching or appending the decoding tokens along with the prefill token from another request. So in that case, you may get higher throughput, but because your decoding request becomes the compute bound, so you'll get higher inter-token latency or lower decoding throughput. So yeah, the root cause is the same as Michael just mentioned.
Yeah, that's a really good point. There was actually a question maybe added in response to that. If you sent the number of prefill tokens to 8,000, what happens if requests greater than 8,000 tokens in the prompt come in? I'm not sure I exactly read that.
If you send a request of prefill token number field, what happens if requests are? Oh, you mean you set a number? I guess you mean if you set a number to 8K, right? So if this is the case, my understanding is if you don't do the trunk prefill, you will just get the invalid request error, because you can also only process like 8K requests at a time. But if you enable the trunk prefill and set the trunk size, for example, like 2K, you can still process this request with the 4 chunks. So that's possible. But whatever the 8K or 2K you set, this has to be smaller than the context length of the model itself, because this is the context length you can process by this model.
Yeah, I think that makes sense. So we have a few more questions that were ahead of time. Yeah, do you see a roadmap from industry chipset vendors adopting FP8 in the AI accelerators? Definitely with respect to FP8. As I mentioned before, this is supported on, NVIDIA latest GPUs from the last, 1 or 2 years and forward, and AMD as well. And additionally, Qualcomm, Microsoft, Meta have all sort of, are definitely going to be supporting FP8 and any accelerators they're making. Going forward, if you're interested in the sort of industry standard, I would recommend looking at the MXFP standard by OCP. I forget what OCP stands for, but it's sort of this general, the X being what mantissa number of bits you're choosing. And this essentially specifies what hardware vendors are going to standardize for, going from 8 bits down to 4, 3, even kind of 2, like FP 2-bit implementations as well. Yeah, there's definitely general public standards on that. And like we mentioned, the vLLM team is definitely talking with hardware vendors on what the hardware roadmap is going to be, so we can, have good day one support for y'all. Yeah, and then here's a question on loading a PEPT adapter and quantizing with bits and bytes. You want to run with QLoRa and run inference with bits and bytes quant. So we actually did start supporting bits and bytes quantization of unquantized models last release. There's some open PRs on loading already bits and bytes quantized models in vLLM. Sort of separately from bits and bytes, we do support running quantized models with LoRa adapters. So if you have a quantized like GPTQ model or FP8 model, running that quantized base model is a separate concern for vLLM than running the, whatever adapters you want to attach onto it, LoRa adapters. So we actually support QLoRa in a more general sense, with more quantization backends. But yeah, there is some beginning support for bits and bytes quantization, although this isn't nearly as performant as running with GPTQ or FP8. So there's a little less interest in developing that. But if you are, definitely reach out and I can point you to some of the PRs so you can join in and test or contribute. And then there's another question on, does vLLM support QLoRa? Generally, yes. There's nothing stopping you, like I said, running multiple LoRa adapters on most quantization methods that we support inside of vLLM. If you're talking about the QLoRa specifically, as in like the paper definition with bits and bytes quantization and LoRa adapters, we do support that. Maybe the one thing we don't support is running like quantized LoRa adapters. That was described in follow-up work in the paper, but we don't really see many people asking for that, since the adapters are already so small. It's not really worth quantizing the adapters themselves and doing inference with that. And I believe that's most of the questions asked ahead of time. So definitely ask questions in the comments as you are, and we'll cover them. Or feel free to come off mute and ask questions face to face.
Hello. Can I ask a question? Here is Yue Yang Pan from EPFL. I have some questions. Probably is not that related to vLLM, but related to Ray and Torch distributed. So currently, I saw RFC on vLLM issues talking about prefilling and decoding disaggregation. So right now I'm trying to write a patch. So I have encountered some problems when I was developing. So one issue was that sometimes I saw a ray worker just ends, so I have to send a SIGQ or SIGTERM to terminate that ray worker. I wonder whether there is a way to get the backtrace when the ray worker received the SIGQ or SIGTERM and it was terminated or not. Because I have looked for some documents about the ray. So what I found was that you can set up a breakpoint in the code to manually trigger a breakpoint, or you can check out the logs for the stuff that is being printed out by a standard out or standard error. But I didn't see how I could get the backtrace, the exact backtrace where the ray worker is executing before it received the signal. I wonder whether there's a way to get that or not.
So in general, I would recommend you using PySpy for this kind of thing. Ray actually has built-in support for that. If you use the ray stack command, it will just run PySpy and output the information for all the workers, and then you see where the different threads are in. Sometimes a library is hanging in some method, and it will give you a stack trace of what's going on.
So could you please do you have a link to that ray stack or something?
Yes, let me see if you make that.
Okay, in the meantime, there's a question from Kyle. Are there plans to support multi-LoRa for earlier architectures like Tesla and Ampere? So actually, multi-LoRa, aka the Pinnacle kernels we have currently, do support Ampere, but not below. There is current work on replacing the Punica kernels with Triton, which will allow us to, JIT implementations for multi-LoRa, and that should bring support all the way down to, V100s and T4s. Hopefully we can get that into the next release.
Do you know what the issue number is for that so I can follow that?
Yeah, let me look it up. There's a live PR.
Okay, awesome.
I might be messing up the presentation, but yeah, you can.
Okay. The other thing, I guess, just to share an update on the OpenAI tool use stuff. We're getting really close. Just working on doing streaming parsers because streaming tool calls is difficult because you have to parse and complete JSON and then diff it against itself and make sure that keys and stuff are ordered in the same places. So that's still a work in progress, but I should hopefully have that PR ready for review in another week or so. So hopefully in a couple versions it should be ready, at least for Mistral and for the Hermes models. But I would welcome any contributions for anyone who wants support for other function calling models. You just need the chat template and to add a custom parser class too.
Yeah, Kyle's been doing great work in the community on this. So definitely if you're interested in tool calling, or I think guided decoding in general, watch out. Okay, are there any other questions?
Yeah, so I have a following question. So right now I'm working on this. I said I'm working on this PR for the pre-fitting decoding disaggregation. So what I did right now is to initialize 2 different word groups with PyTorch, different process groups from PyTorch distributed. But probably I just asked for some advice on like where I should look into. So what I have encountered right now is that within a process group, sometimes what I saw is that the PyTorch distributed gets stuck in broadcast operations. Sometimes it gets stuck in the initialization operations. So I wonder whether there's some. I wonder whether you have seen such problems when you develop the vLLM at like at very beginning or not, and do you have some like materials or like documents on about how I should use this PyTorch distributed properly with different amount of workers or not? Just like probably just ask for some advices on like where I probably can have a look into.
We are also working on similar things like with disaggregated prefill, and also I do provide support for communication. We'd love to get in contact. Like, why don't we take it offline and like just shoot me an email at pcmoritz@Anyscale.
Yeah, sure.
And like I can put you in contact with the relevant people.
I see. That's good.
I'd love to collaborate.
I will just draft the email like very soon and talking about how I am implementing it right now and see like whether you have any advices on that or not.
Yep, sounds great.
Yeah. Sure.
Okay. Cody, is there anything you wanted to cover on the prefix or the prefill conversation? I don't know. Catching up.
You mean that in the chat?
Yeah. Oh no, I see. It's just okay, maybe not.
Yeah, we do have a question in the chat about the prefix caching, the KV cache. I should already answer that question, but if you have a follow-up question, you're welcome to ask here.
It would be, I think, really helpful for a lot of people because I saw that there were some other questions about this too. To maybe put a section in the docs about how those different parameters can be tweaked to and how changing them kind of can impact like throughput versus latency. Because I know that's something I've spent a lot of time experimenting with, is just trying to figure out like which flags are going to be best for my hardware and kind of how they're actually going to impact kind of the different performance characteristics of vLLM.
Yeah, this will be great. Actually, we internally also have this kind of thing. Basically, now you will need like a vLLM tuner to tune those kind of lot of stuff. Prefix caching, trunk prefill, speculative decoding, FP8, FP16, etc., etc. And also you have the block size, trunk prefill size, those kind of hyperparameters. We currently, it's actually hard to say which flag or which value of that flag is actually works the best for your use case, because the use case is very large on very hardwares and on very models also.
And the request, the like type.
Yeah, and the request.
And
the workload, and whether it's like online serving or offline batching, this can be very different. So yeah, we'll gradually, once all those features are getting mature and landed, this is also the direction we're trying to toward to basically try to automatically figure out the best configuration given your request and model and hardware.
Yeah, I think definitely one of the things definitely the thing we have to do first is properly document, what things can be used together. Like prefix caching, like can't be used with like flash infer currently, or, prefix caching or like trunk prefill, like doesn't work with like the FP8 KB cache. So there's like definitely a lot of things here that, you run into sort of clashing, feature compatibility. Part of this like is because we want to get these things to work. It's just there's a lot of things to get working together. So some of these things will get better compatibility over time, but I think definitely to start with, we should at least like have, what options are clearly available, depending on, what backends or quantization methods you're choosing, at the very least, like what features are available.
And maybe also like what hardware or CUDA capabilities, because that's also been a big pain point is, I know like certain things like the LoRa, multi-LoRa adapters are, as we just discussed, only supported for certain, newer devices. And obviously that's a work in progress. But sometimes, I've encountered just like really arcane errors. And, I've had to like really dig through the docs and through the internet to figure out, oh, wait, that's not supported for this particular capability because of the library's implementation. So for certain things where it's like known that it only works on certain architectures or devices, like that would be really good as well, just to kind of prevent unexpected errors at build time or runtime.
Yeah, absolutely. Yeah, that's my my next step. I made a feature matrix for quantization hardware support. So we can now start on those features. Yeah. Okay. Well,
by the way, the most effective way to make this happen is to start a PR, and then that's usually the fastest way to make these things happen.
Yeah. Like if you want to share the information you have, or like at least complain loudly about it, like we definitely see the issues, and like the more people ask about it, the more we care about it. So that's, you aren't being ignored, for sure. There's just a lot to prioritize.
Yeah. So I can definitely make an issue for discussion then.
Yeah, for sure. There was a tweet like this morning of someone running on it that was like also shared internally. So it's building the momentum for sure, this one. Feel free to ask more questions and we can get to you offline, but we'll sort of taper off where we are for today. So sort of last bits to go through. Obviously we want to grow the community here. And if you want to contribute to vLLM, or, report your issues or things, please go to the GitHub, look for like good first issue tags or RFCs that I mentioned in the slides here. And of course, like build examples and demos with vLLM either by itself or with other libraries and LLM tools to get more usage with it and understand how you want to use or contribute to vLLM for features you're interested in. The Race Summit, obviously hosted by Anyscale, is coming in October and has I think, how many vLLM proposals for talks? Like
we haven't finalized the concrete talks yet, but we will soon publish a list, and like there's a dedicated track for vLLM with a lot of exciting talks. So yeah, we would love to see you there.
yeah, definitely sign up and check it out. I'll definitely be attending. Yeah, please join future office hours. If you have any questions or feedback on format, if you want more time for questions or want more details or specific topics, please let us know, and we're doing our best to make these educational for you. Yeah, Neural Magic is hosting a webinar on how to deploy vLLM in the enterprise later this week. So definitely for our enterprise folks that are looking for larger scale deployments, definitely check that out. That'll be hosted by Rob Shaw, our Senior Director of Engineering. Neural Magic is hiring. If you're interested in VLM, working on VLM full-time, or model optimization, or deploying inference scale LLM workloads, come join us. We're hiring. And that's pretty much all. Thank you all for joining. We will share the recording on YouTube within 48 hours, and the slides were shared earlier here, but we'll post them in the various channels. So without further ado, thanks for coming, and take care. See you in 2 weeks.